Hello, welcome to this overview lecture on two sample tests as part of this applied statistics class. We will cover these key chapters in the book by Walpole, Myers, and Ye. And I will in particular talk about tests here. Of course, you could also build confidence intervals based on these distributions, but the main focus will be on testing for the two sample situation. So here's the situation. We have two samples, and we can denote these by x1, 1 up to x1 and 1. That's the first sample. Maybe this is some measurements you do for women. And then you also do some measurements for a number of men. And we can denote this by x1, x2, 1. So that's the first man measured, first man measured. And then it continue up to man number n2. So this will be my sample 1 or the group 1 samples. And this will be my sample 2 or the group 2 samples. And we would be interested in testing if these two samples have the same mean or if they have the same variance. And at the end, we will also get to some proportion data. So then the interesting thing to look at is the probabilities. Are the probabilities of success in these two samples the same, or are they different? And let's go on to the key distributions that we will be using here. The normal distribution is central in all these distributions. It's the building block, and it's used on its own when you are testing the difference in mean values and when you know the variance. If you don't know the variance, you have to plug in an estimate for this variance, and that's when you get the t distribution. And that has various shapes and sizes. And the most popular maybe example is the pooled situation where you estimate the variance assuming the same unknown variance for both samples. When we look at variance values and compare variance in different samples, then we use something called the Fisher distribution, which is again derived from the chi-square distribution. And the chi-square distribution is used a lot when you just have one sample, and then you might want to construct confidence intervals or do hypothesis tests on that single variance parameter. Okay, let's start with an example to motivate this. This is miles per gallon measured for two brands of cars. For the first brand, we have 50 measurements, and we will assume that these are independent measurements. And we see that the average for this brand of car is 36 miles per gallon. For the second brand, there are slightly more measurements. You have 75 measurements, and the mean value here is 42 miles per gallon. So what are we really computing here? Well, for the first one, we construct something called x bar 1. That's the average value from the data samples for the first brand of cars. So then we divide by 50. That's because we have 50 samples. And then we take the sum here over all 50 in that sample. This is the average value or the mean value for group 1 or type A in this setting. And we do the same for the second one, x bar 2, 1 over 75. And then we sum over all samples in this one. And it appears as if brand 2 or type B can drive more miles per gallon. Um, but is this just random variation? We have quite a lot of measurements here, 50 and 70, but it's difficult to say. So a natural statistical question is then, okay, is this significantly larger or is this random variation? And to formalize this, we do a hypothesis test. And this means that we set up a conservative hypothesis 0, that the mean values, or the mu1 and mu2, as we will denote them, are the same for the two classes. And the alternative hypothesis is that it's a larger mean value for type B. And we will then reject hypothesis 0 if there's substantial evidence that this hypothesis is not true. Okay, so if we have a Gaussian distribution here, we can actually do this calculation carefully. And that's what we will try to do here. Here we say that, okay, we know the standard deviation of type A, we know the standard deviation of type B, it's slightly larger. And let's say that these are provided by the brand selling these cars. We know the accuracy of these measurements. And then we can formulate this carefully. So we know here that if we have x bar 1 minus x bar 1, x bar 2, that's the difference between the two observed means. And then we look at the theoretical means, but that was hypothesized to be 0. So if we want to shift this as we usually do in a Gaussian distribution, we subtract here the mu1 minus mu2. But under our hypothesis, this is going to be 0. So we can just remove this part. So it doesn't really matter. It's hypothesized to be 0. So this means that we subtract 0. That's the hypothesized mean. And then we have to divide on the square root of the variance of this difference. So that's what we do in the Gaussian distribution to scale it all to a variance 1. We first shift it with the mean and then scale it to a variance 1. So in this case, what is the variance? Well, we first take the variance of the sample 1. That's 6 squared here because we assume there was a standard deviation of 6. And we had 50 measurements. So we divide by n1. And then we have also some variance for the second sample. So here we take minus x2, but minus, when we take variance, becomes minus 1 squared. So that becomes just a plus. So even though we take the difference, the variance is the sum. That's 8 squared divided on 75. And we assumed independent samples here. So when we take the variance of this difference, there's no covariance, there's no correlation. They are assumed independent. And since we assumed Gaussian independence here, Gaussian distribution as well as independence, this will now be a variable that we can call z. And this z under hypothesis 0 is supposed to be normal 0 mean because we scaled it. We shifted it, and 1 because we scaled it. So that means we can sketch the density here. 0, it's supposed to be 2 minus 2. This is a density function of the standard normal. Okay, so then we can actually check what we get here. This under the hypothesis 0, this is supposed to be a Gaussian random variable with mean 0 and variance 1. If we observe something very large or very small here, it's maybe surprising. And in particular, it's surprising to see maybe this large a mean for type B compared with type A. And if this is then leading to a very surprising variable compared with the standard Gaussian, we reject H0. Okay, what do we get? Then we do the calculations. So we just plug in. We had the, in this case, 40, 36 for the first one, minus 42. That was the mean values. And then we divide on 6 squared, 50, plus 8 squared, 75. And going through this, we get minus 4.78. And is this far out in the tail? I said that most of the probability mass for the Gaussian is between minus 2 and 2. So this would be way down here. And how likely is it to get such a small value, or a smaller value for that matter? So how likely is it that we get something way down here, as small as minus 4.78 or smaller? And this is what we call the p-value of the hypothesis test. And we would then reject, in this case, if this p-value is very small. So for our case here, the p-value is then the probability of observing z smaller than or equal to minus 4.78. And this is extremely small, 0.0000009. So in most situations, we would clearly then reject hypothesis H0. We would say that, okay, this is not random variation. In this case, type B runs more miles per gallon than type A. So that's how we do two sample tests when we know the variance and when we assume Gaussian distributed samples. Going on, if we then say that, okay, we still relate the data to Gaussian distributions, we still assume independence, but maybe it was a bit unrealistic to say that we know these standard deviations. We said it's 6 and 8 for the two different brands. What if they were unknown? What happens then? Unknown standard deviations. So then we say that we have x1 I, which is normal distributed, mu1 and sigma 1 squared. And we have x2j, and this is for I up to n1. And we have x2j, which is mu2 sigma 2 squared. And this is for j1 up to n2. But now we don't know these standard deviations. They are not 6 and 8. And this means that we have to estimate them. We have to plug in an estimate for these variance parameters. And when we're doing so, we cannot use the Gaussian anymore. We have to compensate for this estimation of variance, which leads to more uncertainty. And that's where we get the t distribution. And the t distribution is looking similar to a Gaussian, but you have fatter tails. So in this plot at the bottom, you see a display here where you have the number of degrees of freedom in the t distribution. When this goes to infinity, that's when you have the Gaussian or normal distribution. And this Gaussian goes to 0 faster than these t distributions that have degrees of freedom 5 and 4. And the degrees of freedom here, they are related to the number of samples. So if we have, in this case, N1 and N2 samples, for a two-sample test, we would have degrees of freedom, which is, in this case, equal to N1 plus N2, but we have to subtract 2 because we lose 2 dimensions when we take the average of data, and we take the average to compute the estimate for the standard deviations. Other than using the t-distribution, the two-sample tests have much of the similar elements as we did for the Gaussian distribution. So now we take again this difference in means, and we subtract the theoretical counterparts. So these are the mu1 minus mu2. If we have a hypothesis, we might set this to 0 because we assume they are equal under hypothesis 0. And then we divide on the estimate of the variance. And here there are different kinds of t-tests. And what is shown here is a common version called the pooled estimates of the standard deviation. So here we construct, we didn't, okay, so what happens is that we didn't know these sigma 1 and sigma 2, but we say that they are the same. So we say that sigma 1 squared is equal to sigma 2 squared, but it's still unknown. So we estimate it. And to estimate it, we use all the data we can find. So we take sample variances in sample 1 and sample variances in sample 2. And what is the sample variance here? The sample variance in group 1 is then the average over the samples of the distances from the mean in that group. And then we do the same for sample 2. And then you might see that, okay, this n1 minus 1 cancels here, and it cancels here, n2, and then we're left with a lot of square differences, n1 plus n2, and we subtract 2 here to get the right degrees of freedom. Okay, can we also show an example of this, maybe? Then I thought we could show an example related to strength in materials. So here's a data set with 2 different alloys, and your hypothesis 0 says that these have the same mean, but the alternative says that, okay, this alloy A is having higher strength than B. And we can again go through the calculations, and we can check with tables for the t-distribution with the right degrees of freedom, just like we did for the Gaussian distribution. This is also quite easy to do in software like Minitab, and that's what I thought I would do here. If I bring up Minitab, I have the data set. There are 20 samples for each alloy. And then we can check using a t-test here if this is having the same mean or if alloy A is stronger than B. So then I go to stat on the top here. I go to basic statistics, and then I do the two sample t. And here I have to pick what to use. I have a sample in one of its column, and this is my sample 1 is this alloy A, and my sample 2 is B. And then I see that I have some options here, and one option is to specify a confidence level when I do the test. Should I do this at a certain significance level, and what should this be? And then it's common to use significance level 90 or 95. So we'll just set this as 95. And the hypothesized difference in our case is that the alloys are the same. And the alternative is that they are different. Should we do that, or should we do a one-sided? We should say that the difference is larger, because then we say that alloy A is bigger than alloy 2. Assume equal variances. We will check this because we say that we estimated the variance based on S pooled. There's some graphs. Do we want to take out some graphs? Maybe we can have a box plot of the two samples. And then we just run here and see what we get. And we should get some results here on the top. So here you see the means of each sample, the standard deviation that they had. They might not look that different, 3.6, 3.1. Maybe it's okay to assume the same one. And then it does a t-test, and degrees of freedom is 38, and it gets a very, very small p-value. So in this case, there's again clear evidence that this p-value is so small. So this is significant. There is clearly a difference between these two alloy strengths. So even though the data themselves are overlapping a bit, the mean level of this is so much higher than the other. So this is not just random variation. The mean is different. Okay, so that was something around the t-test and the normal test. We can go on to do tests on the variance parameters. And this means our sigma 1 and sigma 2. And if we just have one group here, so let's say that we have group A, then if we want to do some analysis or some inference on the variance parameter, we use a chi-square distribution. And if we want to compare if two variances are the same in the two groups, we use something called a Fisher distribution. And this Fisher distribution is related to the chi-square. It's actually formed by the ratio of two chi-square variables. So the chi-square distribution is indicated here at the bottom. And it's on the positive side, so variances are always positive. So the chi-square distribution will look something like this. And then we can use this chi statistic to form confidence interval for sigma, or we can reject a hypothesis value on sigma squared if this one is really large or really small, so that it's not subject to random variation, but it's clear evidence. And we will do the same for the Fisher distribution, but then it's formed by ratios of chi-squares because we're comparing variances. So the Fisher distribution is again based on assumptions of Gaussian distributions, and these are independent and they have the same variance parameters and sigma parameters in each group. And then we can call something F for a Fisher statistic. And this is a result of a chi-square distribution with n1 degrees of freedom divided on n1. And then this might be something you use to have the first group, and then you divide on what you have for the second group. And if we look at our chi-square statistic for just one group, we had this chi-square distribution, which was what was that? So let's write this as f, and then we say, okay, now we have n1 minus 1, and then s1 squared divided on sigma 1 squared. This was chi-squared distributed with n1 minus 1 degrees of freedom. So then we divide here on n1 minus 1. That's what we get in the numerator. And in the denominator, we have n2 minus 1, and then the second group variance, and then sigma 2 squared, and we divide by n2 minus 1. And we see that these sample sizes cancel. And what we're left with here is s1 squared sigma 1 squared divided on s2 squared sigma 2 squared. And this is Fisher distributed with n1 minus 1 degree of freedom and n2 minus 1 degree of freedom. And this sigma 1 and sigma 2 is something we don't know, but we can say, okay, under hypothesis 0, they can be hypothesized to be the same. And then this will cancel, and we will only compute s1 squared over s2 squared, and we can check if this is really large or really small compared with what we expect from this Fisher distribution, or with n minus 1 and n minus 2, n1 minus 1 and n2 minus 1 degrees of freedom. Okay, so here you see the Fisher statistic. And of course, this is not only used for testing, it's also used for confidence intervals. So that's good to know. Let's have an example of this as well to clarify a bit how it's used in applications. These are CO2 emissions from cars in the 80s and 90s. So it's way back before they started talking too much about climate problems, but they still knew that CO2 was not necessarily good for several reasons. And for cars in 1980s, there are 20 samples, and for cars in 1990s, there are also 20 samples. And we assume that these are made under ideal conditions. They are independent. These samples are Gaussian distributed with some mean parameter and a variance parameter. And the interest here is to look at the variance. There was clearly a reduction in the mean here, but was there also a reduction in the variance? It looks as if it was, maybe, because 281 squared is clearly much larger than 119 squared. But again, is this substantial? Is it something that's significantly bigger, or is it just something we expect because this is uncertain, this is random variation? Okay, what do we do then under this hypothesis? We compute our F statistic. So F here, under this hypothesis that they are both the same, so sigma 1 squared is equal to sigma 2 squared. Then our test statistic is S1 squared, S2 squared, and this is 281 squared, 119 squared, which is 5.57. And then we can compare this with the Fisher distribution to see if it's if it's really large, or is this something that happens quite often actually in the Fisher distribution? And then, of course, what do you have to do? You have to look at the percentiles in the distribution. And this is what we have done here. We look at the different significance level, and then we move further and further out in the tail of the Fisher distribution with 19 and 19 distribution, 19 and 19 degrees of freedom. So what happens here is that we have this Fisher distribution. This is F1919 because there were 20 samples, for both the 80s and the 90s. And then we see, okay, if we look at only the 5 percentile at the top here, the one that leaves 5% in this direction, so F 0.05, that is 2.16. So if this was our significance level, and we observed F equal to 5.57, that was observed. Our observation is clearly larger than 2.16. So that means at this significance level, we reject. That's what we say here. We reject. And if we continue increasing this significance level here, so this is the 0.01 significance level, we again reject because we end up much higher. So we end up here, 5.57. And the p-value of having something this large or larger is 0.00023, and it's a really small p-value. So this is not subject to random variation. The variance in CO2 emissions of cars was clearly going down from the 80s to the 90s. Okay, so Fisher is important. The Fisher distribution is used, amongst others, to compare the variance between groups and within groups. So this will be important when we start looking at the analysis of variance concepts and also in other branches of statistics. To go on, we'll look also a bit on probabilities. So this is the same setting, but now our two samples are not Gaussian distributed. They are success or failure. So this means that in our group A here, we have indicators I, 1I, which is 0 or 1, and 0 is then a failure, and 1 is a success. And to avoid confusion, then let's not call this I an indicator, let's call it X1I. So this is what we have, but it's no longer Gaussian, this X, it's 0 or 1. And in our sample, we then have X1, 1, X1, 2, all the way up to X1, N1, just like before. It's a sample from group A, and it's similarly a sample from group 2 of N2 samples. What's interesting here is to look at the probabilities. So we assume that P1 is the probability that one of these X1I is equal to 1. That's the success probability in group A. And P2 is the success probability in group 2. So this is slightly more complicated because we're used to the Gaussian distribution. This is not Gaussian, but there is a famous result in statistics saying that if you take averages, they will converge to the Gaussian under some mild regularity conditions. And then this setting, these regularity conditions are satisfied. So we can use the famous central limit theorem and say that the the mean of these trials giving success and failure will converge to a Gaussian distribution. And then the only thing you need is the mean of the samples and the variance of the samples. And since our setting is that of two samples, we can take the mean for each sample and take the difference. And the theoretical mean is then the difference between these two samples, and the variance can also be computed. So here we say, okay, what is our x bar? This is the sample mean still. X bar 1 is the same as we had before. The sample mean of these indicators. And since these were probabilities, it might be easier to say, okay, this is the fraction or proportion of successes. So let's call this p hat 1. And the same for x bar 2. Then we take the average over the second sample. And we will call this p hat 2 because it's the success probability that was estimated or calculated from the samples of the second group. Okay, we still need mu. So what is our mu here? Well, we can compute the expected value of x bar 1 minus x bar 2, and they are unbiased. So this will converge because this is each indicator variable has the expectation P1 or P2. So this will be P1 minus P2. And the variance, what do we have here? The variance of x bar 1 minus x bar 2. This can also be computed from the binomial distribution with success and failure. And for this one, we get P1, 1 minus P1 divided on the sample size in group 1, and then P2, 1 minus P2 divided on the sample size here. Again, we get a plus instead, even though there was a minus here, because minus 1 squared is 1. Instead of saying 1 minus P1 here, some like to say Q's, and you can say Q1 instead of 1 minus P1. It's just a complementary probability, the probability of failure. Okay, so then our Z in this case, the Z value that we are interested in, which will be approximately Gaussian distributed, is x bar 1 minus x bar 2 minus the theoretical expectation. And then we have to divide by the square root of the variance, which is then P1 Q1 divided on N1 plus P2 Q2 divided on N2. And this will be Gaussian distributed approximately according to the central limit theorem. Here the central limit theorem says as n goes to infinity, so that means when we get more and more samples in the populations, this will converge to a Gaussian distribution. And this is really nice because then we can use this to come up with confidence intervals or do hypothesis tests. In a hypothesis test, we would then say, okay, this difference is maybe 0. That's what we're hypothesizing. And these limits in the distribution here, the z alpha half and minus z alpha half, they are percentiles that are now symmetric around 0, just like we are used to in the Gaussian distribution. Okay, so this means that we compute in an hypothesis test. What is required here? We have to compute z, which is our p hat 1 minus p hat 2 minus 0, because the probabilities are the same. And then we plug in something. But what do we plug in? Because we have P1 and Q1 and P2 and Q2, and we don't know these. But in an hypothesis test, we can estimate them. And then we don't get a t-distribution here. It's not like this goes through a t-distribution. It converges to a Gaussian, but it's not a t-distribution for moderate sample size. It's going to something else that we don't have a name for. So we plug in our estimate here for P1 and P2, and we can again use pooling, because under hypothesis 0, they are assumed to be the same. So let's plug in here our P hat and then Q hat, and then we get 1 over N1 plus 1 over N2. And we say that this is standard normal under the hypothesis H0. And how do we get P hat and how do we get this P hat and these Q hats? Well, they're computed by counting the number of successes out of the number of trials. So let's do this in an example. This example is from a production line where you have used previously over the years some tools, and then you see that you get 75 defects out of 1,500 components. And then you propose changes in the tools of the production line. And of course, you're interested in some improvement here, but you check, of course, first if this is worth doing. And now counting the number of defects, you see that there are 80 out of 2,000 components that were tested. So is this something that's an improvement, or is this not significant? So here, P hat 1 is 75 out of 1,500 trials, which is 0.05. P hat 2 is slightly smaller, 80 out of 2,000, which is 0.04. And if we pool these together, we get a P hat, which is then counting the number of defects, 75 plus 80 altogether, divided on the total number of trials, 1,500 plus 2,000. So this becomes 155 over 3,500, and this is 0.044. And we can then compute z, which is 0.05 minus 0.04 divided on this number, 0.044 times 0.956 times 1 over 1,500 plus 1 over 2,000. That's our sample sizes. What do we get? Well, then we get 1.42. And to check if this is large or small, we then compare it with the Gaussian distribution. And that's what we've done here. We see that this z value is plus or minus 1.42. It doesn't matter if we take one or the other first here. And this is not very extreme, because the Gaussian distribution looks like this, centered around 0, 2, minus 2. There's not so much probability mass on the side here. And here we observe something that's 1.42 plus or minus, depending on having sample 1 or 2 first. So the probability of observing something this large is only 0.078, but still this is not an extremely small number. So here it's difficult to reject hypothesis 0 because changing a production line likely induces some extra costs and some changes in the workflow. So you would like to have really significant evidence before you do this. And 0.078 is not an extremely small probability. So this is potentially just random variation. Okay, thank you for watching this. Hope you've learned something about the two-sample testing. Bye.